Okay, there's one more example where we sometimes encounter stereochemistry, and that's in the case of alkenes. Now, you might find it very strange for me to say alkenes can contain the issues of stereochemistry, because when we talked about stereochemistry, we said look for an sp3 hybridized carbon that has 4 different substituents. But there's one case where alkenes have a stereochemical outcome. So let's look at these two alkenes. If you go back through our nomenclature rules, you would find that both of these would be named butene. They're four carbon molecules. There's some kind of butane, but they contain an alkene, so they're butene. And the position of the alkene is at the 2 position. Well, how do you know whether you're supposed to draw the molecule on the left or the right when you say 2-butene? Well, the fact is, butene is not specific enough. This is very much like when we drew the 2 isomers of bromo-chloro-fluoromethane, and we found out there are 2 different structures we could draw. And the nomenclature wasn't telling us which is which. So we had to add to the nomenclature. We had to add, are we looking for the R or the S isomer? Here's a case where we have 2 different isomers, and we need to specify this. Now, as it turns out with alkenes, there are a couple ways people refer to these. Sometimes people refer to this as the trans. Why is this trans? Well, the 2 big groups, these 2 methyl groups are kind of on opposite sides of the double bond, whereas here you might call this cis. So cis and trans, and those are both italicized, so I'll underline them. That's one way to talk about it. But from a stereochemistry standpoint, it's not very precise. As it turns out, it's very easy to draw alkenes that aren't clearly cis or trans, but they have the same idea of isomerism. And this is actually a specific example of, these are diastereomers. They are non-mirror images that are non-superimposable, so they fall under the category of diastereomers. So how do we describe this? Well, let's look at the structure on the left. I'm going to draw it slightly differently. Let's go ahead and put it in the CH3. So how we distinguish this is, what we do is we look at the 2 halves of the molecule. This H and this carbon. The carbon is higher priority. On the other carbon of the alkene, this carbon is higher priority. If they are on opposite sides of the alkene from one another, they are against one another. They are what we call E. And E is short for entgegen, which is a German word. So they are opposite each other. If we look at this structure, cut this in half. Let's look at this carbon over here. The methyl group is higher priority according to the Kohn-Ingle-Prelog rules. On the left, the methyl is higher than the hydrogen. These are on the same side of the alkene, and so these are called Z, and that's italicized. And that's short for zusammen, which is German for together. So this structure would be E, let's put that in parentheses, E italicized butene, and this structure would be Z butene. So just as we saw with sp3 hybridized carbons that have 4 different groups, we introduce this R and S nomenclature system to distinguish them. With alkenes, we need the same thing because we run into this idea of cis and trans isomerization. So we now use these terms, the E and the Z, to distinguish those 2 isomers, which are in fact examples of stereoisomers.